What makes predicting fluid turbulence so difficult in fluid mechanics? Imagine trying to forecast the weather months in advance, but for tiny whirlpools and swirling currents inside a pipe. That's what predicting fluid turbulence feels like. It's a puzzle that keeps scientists and engineers on their toes. Turbulence is not just random chaos. It's a complex dance of countless flow structures interacting in unpredictable ways. This makes it tough to pin down exactly how a fluid will behave once it becomes turbulent. The core challenge begins with the basic rules that govern fluid flow, called the Navier-Stokes equations. These equations describe how velocity, pressure, density, and viscosity work together. But they are nonlinear partial differential equations, meaning small changes in initial conditions can lead to huge differences in outcomes. This sensitivity is what makes turbulence so tricky to predict over time. Even tiny variations at the start can grow into completely different flow patterns. Another reason predicting turbulence is so hard is the wide range of scales involved. Large eddies or swirling motions break down into smaller vortices, which then turn into even tinier fluctuations. This process is called the energy cascade. The bigger structures transfer energy to smaller ones until viscosity, or the fluid's internal friction, dissipates it at the smallest scales. To accurately simulate this, computers need to resolve all these scales, from the large to the tiny. As the Reynolds number, which compares inertial forces to viscous forces, increases, the number of scales grows dramatically. This makes direct numerical simulation impossible for most real-world problems because it would requiring an enormous amount of computing power. In practical engineering, this complexity impacts how we design systems like pipelines, aircraft wings, or engines. Engineers often use turbulence models within computational fluid dynamics to approximate the effects of turbulence without solving every tiny detail. These models are based on assumptions and simplifications, which means they can never perfectly capture all the turbulent features. They are useful tools but have limitations in accuracy. Recent advances involve using data-driven techniques and machine learning to improve these models. These methods learn from simulations at lower Reynolds numbers and try to predict behavior at higher ones more efficiently. Still, fully predicting turbulence remains a challenge because the chaotic nature and multiple scales of turbulent flows are fundamentally difficult to capture. In short, predicting fluid turbulence is hard because it is inherently chaotic and sensitive to tiny changes. The governing equations are complex and requiring vast computational resources to solve fully. Turbulence involves a huge range of interacting scales that grow with the Reynolds number. And current models, while helpful, cannot fully replicate the chaotic dance happening inside turbulent flows. Understanding these points helps us see why turbulence remains one of the most fascinating and challenging areas in fluid mechanics.